Welcome to the Future of SMT Inspection. Really appreciate the fact that you guys took the time to come here. I know you all have very busy schedules. I really do appreciate it. Hopefully this is going to be very informative for you. This is a workshop, so it's going to be, we're going to work together on. If there's any questions or anything, by all means, raise your hand, throw something at us. I mean, I already got 3 kids, so the bottom line is I'm used to being interrupted. Don't worry about it. But I do appreciate you coming out here. When you do a tour through this lab, you're going to find that it's actually a beautiful lab, and that we are very fortunate to have business partners like these that have our machines here. So hopefully this can work out well for all of us. So getting right into it, advances in automated optical inspection technology. Now, just to start out, we're going to kind of go through, most of you guys I know are into contract manufacturing, but we're just going to kind of take this one step at a time. So the first step is we're going to show, of course, a manufacturing line. Now this is kind of a high-end line with everything in it, but the bottom line is we need 3 things to manufacture SMT devices, right? We're going to need some kind of solder paste deposition, whether that be from a screen printer or that be from, perhaps a solder jetting system. The first step is we need to get solder down onto the pads. The next step is we're going to need some form of pick and place, right? Whether it be by hand or whether it be with an assembler, we've got to get components down onto the solder and onto the pads. The next step is we, of course, go through reflow and we end up having connectivity between the devices and the rest of the circuitry. So what this means is we've got multiple different locations where we can have defects occurring, okay? How do we handle that? The only way to really handle that is through inspection. So we can either do that manually or we can automate that. And there's different ways of doing inspection. We can either do inspection continuously throughout the entire line, or we can do inspection at the end when the product comes off of the reflow system. The future of SMT electronic inspection is really going to be moving towards having inspection throughout the entire line for several reasons, okay? 1, we have issues that occur directly at the screen printer itself. So we want to test it with 3D SPI. If we find the defect there, then we can actually modify or we can resolve the defect more inexpensively than if we found it later. The next step where we'd want to have inspection is actually post-placement. Now, if we can find the defect there, once again, before we go through reflow, then it's not like I have to rework. We don't have to rework the board too much. You can use tweezers to turn things, either place things the right way if it's wrong orientation, or place the device down if it's missing. But the bottom line is it's very easy to fix, to resolve the issue post-placement. And for that, you don't really need 3D. 2D will be fine. The next step would be 3D AOI post-reflow. And I'm going to say 3D AOI is really a necessity there just based on what you're going to learn more about with 3D AOI and the capabilities there. Okay? Now we're going to interject something else here, something that's unique, and that is an at-line X-ray system. With an at-line X-ray system, I can take information from our 3D AOI system and feed it to the X-ray and use the X-ray to see issues with devices that I can't see optically. So the thing that's unique here, and what I'm saying is going to be the future of SMT electronics, is inspecting multiple different locations at multiple different locations in the manufacturing line. And the whole purpose for this is because the cost of rework increases dramatically as the manufacturing process flows, right? So if we find a defect here at the screen printer, we can just take and wipe off the solder paste and start again, okay? If we find an issue at post-placement, I can either take tweezers, turn around the device, put a device down if I'm missing it. If I find a defect post-reflow, then I basically have to take it to a rework station. There's chances that I can hurt the board, damage the board, but it's also just, it takes longer, so it gets more expensive. Beyond that, some people are going to have functional test and, et cetera. And when you start getting into some of the higher end testing, that's when some of the dollars really start going out the window. So we're saying that in order to inspect devices, or excuse me, in order to manage your process, achieve lower defect rates, and save money, it's really a good idea to inspect all the way down the line. Now at this point, I really want to gauge I know a few of you guys, I know what you guys have, but let's just gauge the room. How many of you have got a 3D SPI system? That's it. How about post-placement 2D AOI? That usually doesn't go up at all, right? How about 3D AOI? We got a few of those, right? Okay, cool. All right, the bottom line is some of this stuff is going to be new to you. But really, by having 3D SPI, you're going to find that if you can find solder defects ahead of time, it's going to be very helpful for you. The 2D AOI is the one that's always the hole everywhere. But the bottom line is, as you start getting into Industry 4.0, the whole purpose of Industry 4.0 is that you take data from throughout the entire process and you use that to kind of heal the process. Well, now with the advent of 3D AOI, 2D AOI is actually becoming more cost affordable. And I believe it's a very good idea to invest in that because it fills that gap. It actually is going to minimize your cost of rework, and it fills that gap that most people have right now. So anyways, just a little bit of information there. So SMT process defects, here's where it also makes a little more sense with 3D SPI. If we look and we see what defects would occur, you're going to see that the majority of defects are actually going to occur from solder inspection. Here we're looking at about 75%, and I'm thinking that number is pretty much low. You know, most of the defects that people see are due to the solder inspection, or excuse me, the solder process, whether it be at the solder deposition stage where you're not putting down enough solder or you have a clogged aperture, or perhaps after reflow, you have devices that are lifting, et cetera, where you have to take care of that process. So 75% of the defects are due to solder. Here's where I want to get into a little bit about 2D versus 3D inspection technology. And this is really where we're talking about the future of SMT inspection. 2D technology is good. It's been around for a very long time. There's a lot of advantages, a lot of disadvantages, but it's really important that you know those, or at least have those explained to you, because you'll see people, and some of my other competitors are rah-rah, 3D's everything. Yes, okay, well, you still need 2D inspection technology. You can't get away from that. And the reason why is because both 2D and 3D have got their advantages and disadvantages. So really, you need something that's going to blend both. You need two different types of inspection. So if we look at the advantages of 2D inspection, we have one, it's a mature technology. I'll just kind of read them down here. It's cost effective, high speed inspection, very fast. We have the ability to inspect SMT and through-hole technology, the ability to inspect J-lead, less susceptible to shadowing issues, color inspection, ability to inspect tall devices over 5 millimeters tall, and extremely flexible. Now 2D's been around for a very long time, so the algorithms are quite mature. But 2D does have disadvantages as well. I can actually hear myself now. 2D does have disadvantages as well. One, it's incapable of true coplanarity inspection. When we're talking 3D, we're actually going to measure the height of everything on the board, right? So we can actually know how high a device is, whether it's coplanar or not. We can measure the four corners of a large device. We can measure chip components. We can measure solder. Does not provide volumetric measurement data. There's no way to know how much solder volume you have, right? No way to know length, width, and height of a device. You just can't do that with 2D. Increased probability for escapes. I'm sorry, but it's true, right? When it comes to 2D inspection, you're going to have escapes. It's very difficult to manage that because you're using imaging technology. You're just kind of taking pictures and doing comparison. A higher level, perhaps, but there's a better chance of having escapes than if you had a 3D system. Increased false call rate. Anybody who's ever had a 2D system in the past knows that that's just the way it is. You have to add a lot of different images in to allow certain things to pass, certain things to fail. And that's where you end up with a higher false call rate. Now, if we compare that to 3D inspection technology, once again, we got advantages and we have disadvantages. It's not like 3D is a cure-all because we still need 2D. So if we look at the advantages, it's going to be kind of like the opposite of this. Let me go back here. Sorry about that. It's actually going to be kind of like the opposite of what we saw here, right? If I take that and I map it down here. One, we provide true coplanarity inspection, and that's the key thing. So we could tell if an 0201 is lifted, we have 1 micron resolution, but quite frankly, that would be too tight. But we could tell if an 0402 is lifted, 0201, we could tell if a BGA is lifted, we could tell if there's a lifted lead, and we do that using the coplanarity inspection of the 3D system. 2, provides volumetric inspection data. 3, absolute detection of lifted leads and devices. And 4, significant reduction in false call rate. That's because we're actually measuring the device, right? We know the length, width, and height of any device on the board. Sometimes with 2D systems, if you have a black device, it blends in with the board, and sometimes you don't even know if it's missing. So it really is going to decrease false calls. But there are disadvantages. One, it truly is an emerging technology. 3D is still going through its evolution. We've gotten much better at it, but quite frankly, we still have more and more to go. It's incapable of doing 2D inspection for part markings. There's no way to do OCR in 3D unless there's any height to the label or height to the device or whatever. You're not going to be able to see it. So bottom line is 2D is out the window for dealing with part markings. Significant increase in cost. Well, it's coming down a little bit from where it was, but we're still talking maybe 25 to 30% more for a 3D system. It's worth the money though. It really is worth the money with what you get back from these machines. But it is a significant increase in cost. Significant reduction in inspection speed. Now we're talking about taking so many images, it's like 16, 32, 48 images, that it does slow down the process. So the way that we handle that, the way that we combat that, is to have higher resolution cameras that we're trying to capture frame rates as high frame rates, where we capture images as quickly as possible to process those, but it does decrease the speed. There's a significant reduction in speed. Height limitation. This we're kind of overcoming as well, but majority of machines out there can only measure up to 5 millimeters tall. We have up to 25 millimeters at this time. So we've kind of broken through that barrier. Incapable of inspecting J-lead solder fillets, that's simply because they're under the device. So that requires 2D camera inspection to do that. Susceptible to shadowing issues. If there's taller devices like through-hole, there's going to be an issue. And incapable of color inspection. So the whole thing here is, it's a lot of information to go over, but the whole thing is, when you see what 2D offers you, advantages, disadvantages, and 3D, the advantages and disadvantages, one thing becomes very clear. You really need something that's going to be able to do both. You really have to have something that can do both. There's no way to either do one or the other. We've proven that time and time again. The industry calls for a combination 2D and 3D inspection solution. So let's get a little bit into 3D solder paste inspection, okay? So what I propose is that if you don't have an SPI system, that's something that I believe is going to be very valuable to you. What an SPI system is going to be able to do is it's going to give you, if it's a 3D SPI system, which I believe the majority are anyways, it's going to give you the ability to inspect for insufficient solder, excess solder, solder bridging, XY offset, volume, area, height, shape, etc. So when we're talking about the screen printing process, there are some machines that offer 2D inspection modules, 2.5D inspection. The problem is that you can't tell whether you have 1 mil of solder deposition or 3 or 6. And there's no way to really test for the shape of it unless you're doing 3D. So realistically, the 2D solder inspection that you can get on screen printers isn't quite gonna cut it. It's better than nothing, but it isn't quite gonna cut it. So really, in order to ensure that you have the proper solder volume and all these other characteristics are met that you require for a good solder joint, you really want to start out by inspecting right after the solder deposition process, whether it be a screen printer or whether it be a jetting system. Once you know the solder's good there, then you can continue down the process. Another thing that we can do, and by the way, if you are going to be looking at a system, an SPI system, one thing I can tell you is you're going to want to make sure that you have a machine that's capable of dual projection. And the reason for that is we're going to want to look at the solder deposition from 2 different angles, opposing angles, to eliminate shadowing. It's very important. Another thing that we can do here is, once again, keeping Industry 4.0 in mind. One thing that we can do is, by having the SPI system after the screen printer, for instance, we can provide closed loop feedback. So what the closed loop feedback does is, it's not like we're going to control the machines in this way, but if we have an issue where we see that maybe there's an offset trend in X or Y for solder depositions, then what we could do is we can report that over time. We can report that back to the screen printer, and the screen printer can then take that information. It becomes useful information, and the screen printer can either modify where the stencil is to eliminate that issue and to maybe track better onto the pads. But ultimately what we're doing is, this is once again Industry 4.0. We're having the machines provide data to each other. And based on that data, we can then take, and if it's useful data, we can make changes that are supposed to make our process better. By taking in, for instance, if the solder is actually off pad and we see a trend, an offset, and by taking and bringing that back onto the pad, that's going to eliminate processes down the line, right? So once again, closed loop feedback. That's another thing that most major manufacturers of SPI systems offer. Now here, once again, this is the hole in the whole thing, right? The 2D system for post-placement. Now, once again, here we're talking 2D. You don't really require 3D. For 2D, we just want to see, is the component there? Is it not there? Is it rotated? You know, do we have any gross failures like bridging? We can test all that stuff in 2D. We don't need 3D to do that. But when I see people buying 3D systems, and we of course do trade-ins for 2D systems that we've had out there, we got a lot of machines out there, so we'll do trade-ins. My first step, my first question to our customers are, why don't you just take that machine, have you thought about taking that machine and putting it right after the placement machine? And 9 times out of 10 or more, people are like, no, we didn't think about that. It's like, well, why not? Because it makes sense. It's gonna really help you with your process. It'll give you that missing bit information. It'll allow you to take, and if you see an issue post-placement, resolve it right away. So that's something to think about. As far as AOI machine post-reflow, 3D all the way. Now, I'm gonna say 3D, but I'm thinking, you know, I'm gonna say 3D meaning 2D/3D. It's gotta have both. You gotta have to have both engines in there. But really what we're talking about here is the ability to measure anything on the board. These are true measurement systems. This is some of the actual imagery from our machines. Here we're actually able to measure the solder fillet. Here we're measuring the height of the leads. And this is done real time, actually probably about 20% slower than a 2D system, but it's still very fast. So there are challenges that are actually driving and molding and shaping the future of SMT inspection. And those challenges are the products out there, right? So we've got smartphone technology, ultrabooks, tablet PCs. We're talking about very small devices. Everything's getting smaller, right? Phones are getting bigger, devices are getting smaller. So I always, you know, people ask me the same thing. It's like, and we're seeing miniaturization, but the phones are getting bigger. It's like, yeah, not really. Okay, we want bigger screens, but the miniaturization is what drives that screen. We're talking, you know, 0105s all day long. And that is really gating and driving the future of SMT inspection as to what we're gonna need in order to produce good products. So we have those, we have smart 3D, and I'll actually explain a little bit more about this. This is more LED, along with this guy as well, and automotive electronics. These are what I see from my customers, this is what's driving SMT production. So if we look at these trends and we look at the requirement, you know, why do we need 3D inspection? Why do we need 2D, 3D? Once again, the same thing, smartphone, electric vehicle, flexible PCBs, and LED backlighting. So what it comes down to is it's all technological achievements in the electronics industry. That's what's really driving, right? As the boards get more and more complex, we need to get more sophisticated in inspecting for them. That's just basically it, right? So this is having people look at their process and say, you know, what do we need? What do we need in order to do that? And 3D AOI technology is really the way to go with this. Now let's look at some of the trends here as far as miniaturization of devices. This is kind of a little bit of data to back up what I was saying. So this is kind of cool, actually, I love this graph. If we look at 0805s, right? Look at 0805s. As we go from year 2000, this only goes up to 2016, look at how the 0805 package is less and less used as we go down. Isn't that amazing? I mean, I see them every day, but the bottom line is they're being less and less used. If I look at 0201s, conversely, look, 0201s are climbing. And look at 01005s. And I'm sure that these guys are up here for 0201s and up here for 01005s. The 0603 is also declining. So what we have is a miniaturization of packages. And what's driving that? The phones that everybody has in their pockets. Okay? Now, I don't know if you guys have ever, I mean, you guys are probably a lot younger than me, but the bottom line is if I try to look at an 0201 on a board, I'm beyond trying to use glasses to see that. There's just no way in heck. So realistically, we're talking, you need automation. And automation is really what we're talking about here as far as driving the SMT process. So that's smartphone technology, and those are the packages that we're talking about using. Automotive electronics as well. Cars are actually becoming less and less mechanical, right? They're becoming less mechanical and becoming more electronics manufacturing intensive, you know, and that's due to our buddies at Tesla. But the bottom line is here we're getting to the point where because we have so much electronics, it comes down to escapes are a matter of life or death. If you drop your phone, quite frankly, I would kill my kid if you dropped his phone, but that's not the same kind of life or death. But with vehicles, life or death, right? So really we need something that's going to be more robust. And more robust means 3D inspection technology. Another thing which is kind of cool here is we're talking about flexible PCB products. This just makes the inspection, actually the entire manufacturing process, just a little bit more difficult. Now this is actually taking hold more and more, but once again it's throwing a monkey wrench into things and making things a little more difficult, in which case we have to change our paradigm on how we manufacture boards and how we inspect for defects on boards. And then lastly, here we're talking flat panel LCD television. Now if you look around, there are flat panel TVs everywhere. I mean, they're just all over the place. But the bottom line is, I don't know if you know that much about the way these are manufactured, but we require these LED backlight units here. And these LED backlight units are what's actually illuminating in the back, actually is providing the light that provides the intensity and the nice colors that you're seeing. And these devices have got to be placed coplanar. They can't be off at an angle. They got to be really precise in order to have uniformity throughout the entire TV. So we of course have an LED, our MIRTEC has got an LED division, so we are dealing a lot with LG, Samsung, etc. in manufacturing and verifying that these things are manufactured correctly. But these are becoming more and more common. If you notice, there's more LED light bulbs around here. LEDs have got to be placed very precisely, otherwise they're not going to be, they won't look as good, they won't perform as well. So that precision comes from 3D inspection. Okay, cool. All right, so we have a couple of different ways of doing 3D inspection. We've got laser inspection technology. Now, laser isn't really as prominent out there in SMT. Realistically, it's very fast, but there's a low accuracy involved with that. And there's a lot of problems when it comes to dealing with multiple different surfaces of PCBs. The laser gets absorbed. We know that because we had laser systems in the past as well. So ultimately, laser is one way of doing it, but we're talking about used basically for pharmaceutical or food industry. There's also confocal measurement technology. Confocal measurement technology is very, very accurate. It's precise. Unfortunately, it's low speed, but you can actually measure the height of water with a confocal measurement system, which is mind-blowing. So the only issue there is that, once again, it's too slow. High accuracy, but too slow, so it really doesn't fit into the SMT process. The next thing that we have, which is, I guess, probably the epitome for measurement, is white light scanning interferometry. And with this is the most accurate. As a matter of fact, most vendors of SMT machines, of SMT inspection machines, use a WLSI system in order to verify that they're getting good results. These machines are extremely precise, but it would take seconds just to inspect one device. So realistically, this is not going to be able to be used now as far as a common stream SMT inspection system. So that really brings us on to what is the most prevalent system out there, and that is multi-frequency Waring, or sometimes referred to as phase step image processing. What we're doing here is we're shining a pattern or projecting a pattern onto a region of interest. We take multiple images by shifting that pattern. We take an image, we shift, we take an image, we shift. We collect all that data and we characterize whatever our region of interest is in 3D. Okay? So you're going to hear multi-frequency Waring, and that typically is talking about at least 2 frequencies. So 2 frequencies are required to do this. And here we're looking at some devices up here, but the bottom line is you would typically have a low frequency pattern and a high frequency pattern. You combine those, and this is what you get for 3D volumetric data, and that's an 0.005. Okay? We kind of take this another step further here, but what we're going to do is kind of show you we're human beings, right? So the bottom line is I don't want to be showing this to a customer all day long. Customers used to seeing this, right? And operators used to seeing this and used to inspecting in this. So what we do is we take our 2D technology, our 2D camera system, and we overlay the 2D image on top of the 3D image, and this is what the user sees. It's a really clear characterization in 3D of the device, okay? And this actually shows you what the board is actually going to look like, what the device looks like. So it kind of makes it more user-friendly. Once again, we're human beings, so this is just a few more images, and you're going to see that we do have a 15 meg camera. There's a lot of other systems out there that have some high-resolution cameras as well, but the images that these machines gather are actually beautiful, and are really easy to work with, and get easy for an operator to determine whether or not there's a defect or not, and continue on. So, 3D AOI core technology. What do you need in a machine? What's gonna buy you all this? I believe, and I contend, that you're going to require at least some of these things, if not the majority of them, okay? Most of the other vendors out there are trying to at least get to the same level here. One is We have what's called OmniVision 3D inspection technology. What that means is you're going to need a moire engine. The bottom line is a moire engine, okay? We have a little bit something different. We use blue DLP projection technology. I'll explain what that's all about. We have a 15 megapixel camera, 8-phase color lighting system for 2D. Of course, you need a precision drive system and side view cameras. I believe you're going to need all this in order to contend what you're going to have to work with in the future, or what you're working with now. Some of you guys got some pretty high level stuff that you're working with right now. So we'll take it step by step. When we're talking about digital tri-frequency moire, that's something that MIRTEC coined, tri-frequency, that means that we're actually using 3 frequencies, which allows us to characterize anything from 0 to 25 millimeters tall. The way we do that is we've got a single projector. We have actually 4 projectors on the head, but we have a single projector which is capable of sending out low frequency, medium, or high, because we're digitally controlling that. There's 2 different ways of doing moire, analog or digital. The nice part about digital is all we have to do is just change the pattern. And when we're talking about dealing with taller devices, we have to have a lower frequency. So what we're using is medium and high frequency for doing devices characterizing devices up to 5 millimeters high. And then for looking at taller devices, we use low frequency and a medium frequency, and that characterizes devices up to 25 millimeters tall. Okay? So we're just going to give you, kind of drive this thing home. There is actually 4 projectors on the head. We have low, medium, and high frequency. So that means we're taking 12 images per device. Those 12 images per device have got to go down, got to get processed. That's what we're talking about, having some higher level processing. And this is just going to show you one more time here. So 12 images there, projector 1, 2, 3, and 4. Okay, so we can characterize anything on the machine, or anything on the board. The next step is, once again, here's an advantage. We're talking blue DLP projection technology. So what we're seeing is that we have a lot of wafer level devices that are becoming part of the manufacturing process. A wafer level device is going to be kind of like a die, and these die are like shiny little mirrors, okay? So ultimately what ends up happening is the light reflects away from these. So in order to contend with that, we introduce what's called blue moire. And what the blue light does is it allows us to characterize the device. For instance, this is monochrome. This is what a lot of my competitors will have. And switching to blue moire, this is what we're getting back. So here, when we're dealing with these kind of images, we have to do a lot of manipulation of the data. We have to do a lot of filtering. Whenever you do filtering, you're either adding in data or removing data that shouldn't be there. So quite frankly, it's kind of lying a little bit, but ultimately the blue moire allows us to get more information and characterize the devices correctly. So it's just an advantage. Next step, 15 megapixel Coexpressed camera. The reason for this, once again, is speed and accuracy. We of course manufacture our own cameras, but ultimately you need a high resolution camera, whether it's our machine or not. We were also the first to introduce Coexpressed camera technology. It's been around for a while, but Coexpressed camera technology means that we can actually process data much more quickly at 25 gigabits per second, very fast, versus camera link, which is standard at 5 gigabits per second. It's maybe 5 times faster. But the reason for that is we're taking 48 images at times, right? At 48 images, we got to process all that very quickly. So we need to be able to do data transfer rates very fast. And once again, it comes down to speed. Speed and, of course, accuracy. So, you know, MIRTEC versus competition. Here's where we get to tout the fact that we have a high resolution camera at 15 meg. Another thing here, this kind of always drives me nuts, but it's very important to understand this. Telecentricity. I don't know if a lot of people know what telecentric lenses are and the difference between them, but ultimately we do because we've been dealing with telecentric lenses, conventional lenses for years. So here if we look at the theory behind a conventional lens versus a telecentric lens, we see that there is a parallax effect or distortion that occurs with a conventional lens. So we end up getting kind of like a fisheye look for this, and it looks like objects that are toward the edge of the frame, we're looking at the sides of those devices. If we're looking at these cylinders here just as a representation, and they're all the same size as far as the diameter go, if they're taller or closer to the camera, they actually appear larger. Telecentricity removes all that. It's really important to have a telecentric lens because we have got to do testing and we have to inspect and come back with length, width, and height measurements. So unless you have an accurate means of inspecting for that, you're kind of losing right off the gate. Now that's theory. Now taking this into reality, if we look here, this is an aluminum electrolytic cap. And if we look at this here, that's with a telecentric lens. First, you can see that it's, you can read the writing, which is clear. Secondly, if you look at this guy here with the conventional lens, see how it looks like it's crossing over the screen printing? And over here it's not? That's because this object is tall. And objects appear taller as they go closer to a camera. So if I inspected this and I wanted to come back with a diameter measurement on that, I'd be wrong. That's why you need telecentric lenses. Now once again, we deal a lot with 2D as well. So there's certain things you have to use 3D for and certain things you require 2D for. And that's where you really need illumination. Color really does a lot for you. There's a lot of machines out there that are still monochrome. So the 2D inspection engine really requires good illumination. Easy for me to say, huh? Good illumination. We're also going to talk a little bit about side view camera systems. So the purpose of a side view camera system is to deal with things that we simply cannot see with a top-down camera, right? We can't see under J-leaded devices. We can't see the edges or the sides or writing on through-hole devices. That's where we really need to have a 2D camera system at an angle, right? It just kind of shows you, just take it home where you look at it. So here we're talking about having the cameras there, and you're going to see some of the information that we get. And this is taken off of one of our 10 megapixel camera systems. So for looking at the J-leaded devices on this PLCC, we can test for all of the solder joints, whereas if I'm looking top down, I simply can't see those solder joints. Also, if we're looking at side view camera and we're looking at a through-hole device, I can read the writing on it. I can do OCR recognition on the device. So it's kind of a necessity. Once you have the board in the machine, you want to inspect the hell out of it. Anything you can inspect, you want to inspect the hell out of it. And once it leaves the machine, you don't want to touch it anymore, quite frankly. You want to have the machine tell you if there's an issue or not. So it comes down. Precision AC servo drive technology, ultimately you got to have something that's going to get you the accuracy and repeatability. That's of course a requirement, especially as these devices get much, much smaller. So we need extreme accuracy. So for looking at this device here, our repeatable results, we're getting robot accuracy of 1 micron, repeatability of 10 microns. That becomes extremely important when you're looking at 01 and 05s, because we're also testing these devices to see if there's an offset to them or not. Now, here we're talking about the machines are great. And of course, the machine's supposed to do a good job and work for you. But you also require ancillary software. And what I suggest is that you folks who are actually manufacturing these PCBs rely upon your vendors for this ancillary software that's going to make your life easier and make your process better. So things that can actually maximize your efficiency is what you're looking to do. Some of the software costs a lot. It costs a lot to develop. You know, people always say, geez, it costs a lot of money for a CD. It costs a lot to develop that CD. But ultimately, things like offline debugging, remote repair, remote SPC, total remote management, and IntelliTrack, these things really make your life easier and once again, get the most out of your SMT process. Especially when you start looking at adding SPI systems, 2D, AOI post placement, 3D AOI post reflow. This ties it all together, okay? And probably, that'd be fine. Probably the best buzzword that you're gonna hear out there is Industry 4.0. So what that really means, just to characterize that again, what Industry 4.0 means is that we're taking information from all the machines within the manufacturing line. And we want to take the usable information, because there's going to be a lot of information that's not really usable from machine to machine. But we want to take the usable information and use that in order to refine the process. We want to take a snapshot as to what's going on and help refine the process and basically add value to the process and cut down on rework. There's a lot of things you can do, but it all comes down to data, and data comes from connectivity. We need to be able to connect all the different machines, collect the data, and then use what we can from machine to machine. Like I described before about the placement, the SPI machine and the screen printer, being able to take and feed data back to the screen printer in order to modify the process. That's very important. So one of the things that we're looking at here is connectivity, and this is definitely the future of SMT inspection. Definitely the future of SMT manufacturing is Industry 4.0. And Ragnar will hit on that as well. We'll show you a little bit about what we have here in order to help our customers. But ultimately, we've got screen printer, SPI, pick and place, AOI, reflow of an AOI, and all the machines are communicating to each other. They are all connected. We've chose to connect them through Coexpressed, which is a platform that actually is, they can communicate with almost any machine out there, whether they be old or new. A lot of newer systems have different things like CFX. Ragnar will go through that as well. But you have a lot of older systems out there as well. So we chose to use Coexpressed for that connectivity. It works very well. So that's what we're talking about, is being able to communicate and use data from machine to machine. And this is probably going to be the thing that everybody's going to be learning more and more about, right? So here is our MS11E. This is our SPI system. It uses 3D dual projection Waring in order to determine if we have good solder deposition on all the pads. So we have our test board in here. I'm going to go ahead and run through this test board. And what happens is we go through each frame looking at multiple different solder depositions on the PCB, and we're looking for volume, XY offset, bridging, shape deformity, basically looking to make sure we have good solder depositions across the entire panel. Once this is done, we're going to go through and hit the review button here and look at each one of the different anomalies that the machine has presented to us. Here we're looking at a pad which doesn't have any solder on it, and as we step through the anomalies, we see that we have bridging here, bridging between pads, and we're also looking to see if we have sufficient volume. Once we collect all this information, this now becomes available to my offline PC. And that's where we're going to actually have a chance to show the operator what happened at the SPI system. And this is our MV6 Omni. This is a 3D AOI system. This machine uses a 15 megapixel camera and digital tri-frequency moire. We have 3 different frequencies that we use to capture and profile all of the different components on the board in 3D. Tri-frequency allows us to go anywhere from 0 to 25 millimeter components in height. So what I'm going to do here is, this is our test board. We have quite a few anomalies on there, or defects, quite frankly. And what I'm going to do is go through and run it. And as I run this, we're actually we're going from frame to frame, and we're verifying whether or not the components are there. We're verifying the proper length, width, height, and also coplanarity of all the components on the board. Once the machine has gone through, it's going to present the operator with a set of anomalies. I say anomalies because at this point, we go through and classify whether there are defects or not. So here we're going to hit the review button, and then we step through each one of the anomalies. Now at this point here, we can tell definitely that we're missing a component. So I can classify that, if I would like, down here as being missing. Now the way this works is we're also going to be presenting this information to our X-ray system. So what I want to do is I want to classify those regions of interest that I want to do an X-ray test on. That would be post AOI. So if I look at, for instance, there's a BGA that we have that there's a defect on. That'd be right here. So this is a BGA. Now it's a bottom terminated device. If I look at what the machine has called out, the 3D AOI is saying that this location here, that corner, is actually raised. I really can't tell what that looks like, once again, because it's the bottom terminated device, and I can't tell really what happened. Perhaps it was a process issue, perhaps there's something underneath the device. So at this point, what I'm going to do is classify this as smart loop. What that means is, now I want to be able to take that and look at that at the at-line X-ray system. And this is our offline PC on which we're running our IntelliTrack software. What we've done is we've collected information from the SPI machine and from the 3D AOI machine, and we've also collected information from our at-line X-ray. And that is presented to the operator in one screenshot, which allows them to kind of figure out where the process went wrong. If you recall that BGA that we saw that was lifted, well, here we see that the X-ray system shows that there was actually an 0201 device underneath the BGA, which caused that corner to be lifted. So basically what we're showing here is our 3D SPI shows us all of the solder bumps that are there. Everything's good as far as solder goes. Our 3D AOI is showing us that that component was defective, but really we could not tell anything until we put it through the at-line X-ray to determine exactly what the root cause of the issue was. At this point here, the board would go to rework, and we would remove that device and then basically place the device down again and make sure that we can make the board work properly.